So let's go through a history of some of the projects I've worked on, and I'd like to lead you along from step to step as to what I did, what I found, and what it led me to next. Nowadays, we would call projects by version number. I've used the words Mark 1, 2, 3, 4, 5 for mine. Starting with a Mark 1, I didn't count that little train track motor as we went along. Starting with a Mark 1, I saw that three-stage nail shooter, and I wanted to build a three-stage coil gun here, and I built 3 coils that would be energized in pairs. That is, there's the first 2 coils would get turned on for a certain length of time, and as the projectile got pulled toward the middle of it, I'd turn off the first coil and turn on the 3rd coil. It would get pulled further along, where I could turn off the 2nd coil, leave the 3rd coil on for a short time, and hopefully it would fire on out. You see here timers and counters on the left. There's a bunch of switches where I could compare the counter with a certain number, and if I turn on and off these coils in a predetermined sequence. However, this worked very poorly. The results were wildly variable, mostly depending on starting position, but I found there's no way, even as carefully as I could set the initial starting position, it was still variable. And the bottom line here is that the coils here are extremely sensitive to the position of the projectile. So fixed timing without some way of detecting the projectile as it moves is really never going to work. And as a side point, these coils here have so many turns. The inductance is proportional to the square of the number of turns. So the inductance here was quite large. And inductance is the tendency to resist change in current, and it slows down the speed at which you can turn on and off the coil. That led me to try to figure out what size coil really would work best in here. And in the Mark II, it was a kind of a side project. I wound a coil with a bunch of layers, 14 in this case, and between every other layer, I'd bring out a loop of wire, connect it to the terminal strip, and go back and wind some more turns, down and back, bring out a loop, down and back, bring out a loop. In theory, I was thinking that and expecting that using all 14 layers would provide the best results because it would have the most turns per inch. And the more turns, the more magnetic force you have. In practice, the best performance happened with only 2 layers. That is the very minimum available in this particular mashup. And I determined the conclusion was that the extra layers add a lot of resistance. And remember that inductance is the square of the number of turns. It added a lot of extra inductance. Physically, the extra turns being further away have less effect on the projectile as well. So this was good. Ever since, I've been winding coils that have just 1 or 2 layers of very heavy wire. You might notice here the firing tube down the middle of this is brass, and this was later found to be a very poor material. Brass, being conductive, would also have induced eddy currents. And this is the principle of, in one sense, I built a transformer. There's a primary, which is outside a 1-turn secondary, and the secondary is shorted. That is, you can conduct current in a circle around the surface here. This is a transformer with a shorted secondary that all it does is waste energy, a considerable amount, upwards of 20 or 30% in this particular case. Having learned something about the coil, I wanted to understand more about the magnetic flux path. That is, what direction in space does that magnetic flux travel, and how can we improve it? The experiment here was another single-stage coil gun, happened to be built in a toolbox in the local hardware store. The area of interest was that copper coil on the right, and I took leaves from an ordinary transformer, separated the leaves. Each one is in kind of an, imagine an E shape, And I pointed the E's toward each other and stacked them around the firing tube, put the coil in the middle, and the idea is this outer iron would conduct a magnetic flux into the middle, which is where we want it. It's a magnetic guide, as it were. And this turned out to be extremely efficient, higher than almost any that I've seen on the web, with a caveat that this is a very low-power coil gun. It runs with a couple lantern batteries that are underneath that wood shelf. There's the same stud-type SCR. You can see the copper, the shiny copper braid coming up on the right-hand side, up from under. And it's low speed, but it's highly efficient. One thing I observed on this is after it fired, it would leave a negative voltage on the capacitor underneath there. And electrolytic capacitors are said to be sensitive to negative charge. It tends to change the ion layer that's on the surface of the plates in there, hence the word electrolytic. And I began to get interested, am I actually damaging the capacitor? And what can we do to avoid ringing? So I built another little more refined coil gun here. My goal was to start scaling it up to more energy and launching small diameter nails down the tube there. And to explore critical damping in here, I put a series resistor in the high current loop. And you'll see that as some diagonal lines in the lower right. It's a zigzag shape. Turns out it needs a tiny amount of resistance, a fraction of an ohm, and that could be built by taking a piece of, again, magnet wire of a certain length and a reasonably small diameter. Turned out to be only about a meter or so of magnet wire here. It gave the necessary resistance, and the goal was to insert just enough resistance so that it wouldn't ring to negative voltage and thereby protect the capacitor, but not so much resistance that it would damp out or slow down and reduce the efficiency. I learned from this coil gun, first it had poor efficiency, largely because the diameter of the nail that I was shooting was saturated with magnetism, but also I came back and did the mathematical analysis. There's an analytic solution that allows you to compare a completely undamped coil gun to a critically damped coil gun circuit here. And it turns out that in that analytic analysis, the peak current that during the discharge is reduced by 64% compared to a completely undamped, zero resistance coil gun. Well, that's bad. So after this, I have completely eliminated all resistance possible. That is, it's not zero. There is resistance involved in wires and connections, and even inside the capacitor itself. Obviously, the coil has resistance, but my goal from here on out is to use heavy wire, small number of turns, solid connections, and so forth. And I'm happy to say that in the years I've been doing this, as far as I can tell, I have not damaged any capacitors whatsoever on here. So they haven't failed me yet, but the jury's still out. Come back in a few more years. In this coil gun, I was looking at that silicon-controlled rectifier switch at the end of that heavy, thick red wire, and wondering what effect SCR may have on the discharge pulse, and if there were other solutions. At this time, I came to a coil gun I'll discuss in a minute, done by Discovery Channel, and they had a novel idea about a copper switch with low resistance with some very attractive features. Now, the copper wedge to close a circuit, the idea is that the wedge itself has no wires on it. It's closing a circuit between two other copper blocks. And behind the wood panel, the white sheet of paper you see here, is the electrical connection behind these copper blocks. It would complete the circuit between the capacitors and the coil that will go up on top. The idea here is attractive. The concept is a wedge of a certain angle will close and lock in place. A narrower angle, it will lock in place and be difficult to remove. And a wider angle, the copper, when it drives in, will bounce off and come back. At a certain critical angle, which works out to be about 8 degrees in copper, when you drive that in there, it will lock in place without bouncing. And testing at low voltage with an oscilloscope found that it has excellent electrical characteristics. It actually does not bounce. But if you look at the bigger picture here, a keen eye will notice there's not actually a coil up on top of that, and the project is not done. This is some more work I have to do to start firing this at higher energy. The Mark V is intended to be a low-speed projectile, working away from those narrow nails. I'm working with a 3/4 inch diameter bolt, 5 or 6 inches long, and I'm interested to see how much energy it gets. The idea being the speeds will be lower, but the energy will be higher because it has greater mass. Well, there's additional work to do right there. And looking ahead, I have parts for another project, and that would be a 5-stage coil gun. Again, large diameter bore. And here, this particular one has optical sensors in order to run all the stages. And this happens to be parts that I purchased from a retired coil gun that was originally built at the University of Toledo. And I hope to rebuild this. It's not nearly in the shape as you see in the first picture here that he sent me. I just have a big box of parts, and once I finish some other things, I'll have time to spend some significant engineering effort needed to get all this together. And since they built theirs with discrete logic, we have improved technology with microcontrollers such as the Arduino and the like that have promise in this application. But as of this day, it's only a box of parts and will be future work someday. I'd like to tell you about one more project that I worked on, and that is the Discovery Channel. Put together a series of episodes called alternatively Engineering the Future or Saving the Planet. All of the episodes were involved with trying to solve the huge engineering problem of global warming. This particular episode examined a cloud of lenses, trillions of these 1 meter across diameter lenses, floating in space at the Lagrangian point, a stable point between the Earth and the Sun, that would reduce the amount of incident light on the planet and thereby reduce global warming. Well, how do you launch trillions of lenses? You don't do it with chemical rockets. That's not economically feasible whatsoever. But perhaps a magnetic launch could put all these into orbit. In this television episode, they built a coil gun. They were trying to prove the concept that they could gain 1,000 G of acceleration, at least over a short distance, to help reinforce the idea that perhaps one could build a very long coil gun to reach the escape velocity needed. This particular model, it looks like an alien lander. All the assembly work was done by a highly talented team of special effects engineers. I was hired to do a little contract advice and consulting on the side here. But what you see here is not my work. It's primarily Discovery Channel who did a great job. And from this particular coil gun, I got the engineering concepts for that magnetic switch. So that takes us through the main coil guns that I've worked on so far. Let's talk about some things that come next and what you might be able to do to build off of this work.